real examples of material, but they are models. We don't use the word toy model every time we use the word model, and they are, right? Okay. So this is your toy model for this triplet of elements that define your model. According, if you want to describe possible characteristics of biological life. But as you say, now you have proper definition. You have, and then you make predictions, which are summarized in these three scenarios. Right. And those are, especially the third one, is the one which is really remarkable.
Yeah. Okay. So, in other words, for a statistical physicist who works on critical phenomenon, this looks reassuring. The fact that you get a power law like this suggests that you have scaling here, and it looks how do you say, reassuring. Well, that's great. I'm delighted to hear that.
And you use the other two to compare.
Yes.
To appreciate the scaling.
Right. Terrific. Okay. Great. Now, okay. Before starting on the technical side, though, there is some conceptual stuff that I think would be fun to mention, which is the main purpose, as far as I'm concerned, of this whole model is creativity, to understand the question of biological creativity, generation of novelty, innovation, where new genes come from. Now, in my model, it sort of just comes out from the postulates of the model, right? This is how to interpret this, that you are getting biological creativity, you are getting evolution to take place. But what about in real biology? That's a different kettle of fish. In real biology, most people don't think in terms of creativity. It's even politically incorrect to talk about progress in evolution. You know, to say that a human being is somehow superior to an amoeba is racist, I understand, in the latest, you know. Anyway, this is supposed to be a joke, don't look frightened. But it's true that under the current way of thinking, it's popular to say that an organism adapts to its environment until there's a perfect match, at which point evolution stops, until the environment changes, right? So that's the normal way of thinking. And I think that's the wrong way of thinking. The right way of thinking was actually discovered by a biologist who unfortunately passed away, but full in years, last year, called Lee Van Valen at the University of Chicago. And it's called the Red Queen hypothesis. And it's a very profound idea, and it's the reason that really drives creativity in real biology. And what is the Red Queen hypothesis? First of all, the Red Queen is a reference to children's literature in the English-speaking world. It's Lewis Carroll's Through the Looking Glass. Not Alice in Wonderland. The more interesting book is Through the Looking Glass, the second one. And the Red Queen, it's a chess game. Alice gets involved in a chess game, as a piece on a chess game, and the Red Queen is the wildest character, actually, in the whole story, and she makes a remark to Alice that you have to run as fast as you can to stay in the same place. So in other words, it's an arms race. The idea is the following: no organism is isolated, even if the environment doesn't change, even if the climate is fixed and the geology is fixed and the temperature is fixed and all of that. Even if everything that you can see looks like it's constant, there is still a tremendous, drive? No, it's, there's a word in physics, but I don't know what it's called. Yeah, well, I don't know what it is. There's a better word. I don't remember English anymore either. There's a tremendous driving force in the direction of creativity, which is that you are part of an ecology. There are bacteria that can make you sick. There are bacteria on your skin. There are bacteria in your intestines. There are viruses that can kill you. You're living actually in harmony with all of this most of the time. You know, there's a jungle on your skin and in your intestine, but in fact that works. It's a relationship which helps everybody involved most of the time. Things go wrong occasionally, but usually it works. But the point is, also there are the animals you eat. Normally they're ones that are smaller than you are, and they're the animals who eat you. Normally they're bigger than you are, right? The rule in ecology is everybody is somebody else's lunch. Okay? So the point is, all of these creatures are evolving due to random mutations. They're all trying different combinations. And if you think of these bacteria as harmful, they're looking for ways to, that your immune system can't stop. And the animals that eat you are looking for better ways to catch you, and the animals that you catch are looking for better ways to escape, to changes in their DNA which enable them to escape better from you. And so basically everybody is evolving, and you have to keep evolving to keep up. And the example of this is that in my lifetime there have been many diseases that have suddenly appeared and that people have been rather scared of. AIDS is one of them. There was a kind of, in fact, the situation now is that a lot of antibiotics don't work, and you're starting to get what are called superbugs, which are bacterial infections which no known antibody can stop. You see? So that's an example of this. And it happens very quickly. It's happened in my lifetime. When the first antibiotics came, the bacteria were helpless. but they didn't stop evolving. They very quickly have figured out how to survive with all of some of them know how to survive with every antibiotic that is known now. Well, there's one antibiotic they try to use very little, which is the sort of the last resort, right? Because if you use it a lot, then the bacteria will learn how to be immune. So this is an arms race, The U.S. won against Russia, if it won, basically because the Russians went broke. They couldn't spend enough money the U.S. and Russia didn't fight a war, but the Russians couldn't keep up with the expense on armaments that the U.S. could. So it's an arms race. So this seems to be the fundamental reason. And of course, another joke is, since we've been talking about jokes, is this is the greatest piece of work that Lee Van Valen did, and of course he couldn't get it published. It was rejected every place he sent it, so his response was simply to create a new journal, start a new journal, and publish his article in his own journal. This piece of work, I'm pretty sure that this is considered now absolutely mainstream, even though at first it was rejected, because I've seen John Maynard Smith, who is greatly respected, praise it. And in fact, this has to do with a whole question of interpreting Darwin's theory. Dawkins talks about the selfish gene. And there's a problem with this view, if you believe in the selfish gene, and in traditional population genetics, if you want to do this technically, that there shouldn't be sex. And in fact, almost all species of animals are sexual, not parthenogenetic. And there's something called the twofold cost of sex in population genetics. Well, in intuitive terms, if the genes are really selfish, why should you throw away half your genome? Which is what you do when you have sexual reproduction. So the reason that looks hard, and John Maynard Smith says it very clearly, he says everything very clearly. He said there must be something fundamental we're missing, because according to our theories, our population genetics, sexuality should be very disadvantageous. And it's almost universal. And then he welcomed Lee Van Valen. Apparently there are many reasons for sexuality, but I think the main one is the need for creativity. And what sexuality does is increase the speed of creativity, because you can take new genes from both parents and combine them in one organism, which otherwise everyone would have to reinvent them all on their own. So it's a way to take good things and share them. Okay, so this is the reason, apparently seems to be the real reason for creativity, for the exuberant creativity of nature, which I don't know if you saw any of those illustrations when I went through the book on Monday, Ernst Haeckel's art books, they're about a century old. Okay, so now the question is, so that's why there's creativity in real biology. Now how about creativity, how about these results in this model? Well, the mathematics you need for this is algorithmic information theory, and all of the math was really there in place, all the necessary tools were there in 1975. So anyway, this is the technical paper. I have this book coming out, Proving Darwin, And I have this technical paper coming out, both supposedly in May of next year. The technical paper is called Life as Evolving Software, and it's going to come out in a book edited by Hector Zenil called A Computable Universe. And let's go to the appendix where I try to give a summary of algorithmic information theory in the hope that this will help people who are outsiders to be able to take a look at this paper. So where is the appendix? Here it is. Okay. So, now notice, this is a field which talks about a complexity measure, a measure of information content, which is the size of the smallest, size in bits of the smallest program to calculate something. I'm not applying this to organisms directly. Okay? The DNA of an organism is not the most concise program that produces that organism. It's not. There is some connection, but it's not. Where I'm really applying this theory is in the mutations. The key conceptual issue, it seems to me, is what is a mutation and what is the probability, a priori probability of a mutation. Okay, just wanted to warn you about that.